you can look forward to that at the end afterwards within the next upcoming day or two. I'd also like to talk a little bit about the slide that you've been staring at, perhaps for a couple of minutes, or for the one gentleman who's been staring at the screen for 9 hours. Hats off to you. You win the prize for the longest wait. But you can visit via our QR code there, Clean Coders Studio. We now offer software development for your projects globally. Feel free to reach out to us, and we'd be happy to talk to you about your upcoming software project and how we can serve a vital or a little role in that, and we'd be happy to assist you with that. Without further ado, we are going to turn the time over to Robert Uncle Bob Martin for today's talk on the future of programming languages at the confluence of paradigms. We look forward to the talk, and we thank you again for joining us, and we'll catch up with you at the end. Bob, take it away.
All right. There. Okay. I'm pushing buttons here, and I think things are starting to work. Let's see. All right. Yeah. All right. And I think we're muted. Okay, good. So you all hear me okay? Just give me a high sign if you hear me. Say yeah. Okay. Oh, all right. Thank you. Whoa. All right. So good. Let's get rid of all of those, and let's start this talk. I believe my screen is being shared, so you should now see the future of programming languages at the confluence of paradigms. So this is a talk that's been kind of bubbling up inside me for a while. It's a mixture of software history and software projection, where we've been, where we're going, and in particular, what's going to happen to our languages. And if you look at the language scene right now, you see a lot of churn. It's always changing. There's always some new language coming out, whether it's Swift or Dart or whatever. I'm not going to go through them all. Where is that taking us? Where is that going? We're going to try and plot that trajectory over the next 2 hours to see if we can come to a conclusion about where this really is all going. But to start that trajectory, we're going to go back in time. And this was my very first computer. I was 12 years old, 1964. My mother bought me this computer for my 12th birthday. I was always kind of a nerdy kid, a science-oriented kid. I liked all kinds of science and stuff. And so my mother was hunting around for some kind of scientific present. And here's this little plastic machine that she got me. If you look at it carefully, you'll see it's got 3 bits. So, you know, it can store a number as large as 7. And I learned octal on this machine, obviously. It's 3-bit octal. If you look carefully, those vertical metal bars, those are AND gates. They can sense the position of the 3 bits. And you program this machine by putting little white tubes, or in this case, they look black, right? But little tubes on the pegs of the flip-flops that'll block those bars from sliding in. If they do manage to slide in, they engage a mechanism that changes the state of one or more of the bits. So in essence, this is a 3-bit finite state machine, which I learned to program in 1964. And I fell in love with the entire concept. You know, after a few months of fiddling around with this machine, I realized I could make it do anything that a 3-bit machine could do. And I fell in love with the concept. And then, of course, I wanted more bits. Now, other people wanted more bits, and they wanted more bits before me. So what languages were they programming in? I programmed this machine in raw Boolean algebra. I had to do the Boolean algebra math to figure out where to put the pegs on those, the tubes on those pegs. But there were other people dealing with actual electronic computers going all the way back to 1946. And what did they program in? And the answer to that is they programmed in binary, because what choice did they have? I mean, there were no languages. There was only the machine code, right? And if you've never programmed in machine code, you should try that just so that you know what it's like, right? Find some emulator on the web, some 6502 emulator or 8080 emulator or PDP-8 emulator, and see if you can write a very small little program in pure binary. And that will give you a fair bit of respect for these people who were doing that in 1946 and 47 and 48. In fact, even into the 60s, there was a fair bit of just raw binary programming. I remember as a programmer in the 70s, there was a guy who tried to bring it back. He tried to bring back binary programming, saying it was the only true way of programming. And I read the paper that he wrote on that, and then I felt very, very sorry for him. I bring this one up because when I was a freshman in high school, they wheeled in an electronic computer. And it was this one, this ECP-18 computer. They wheeled that thing in, and they put it in the math lab. And all the math teachers got to play with it, and I didn't. But I was able to look over the shoulder of the people who were programming it. They brought some techs in from the company that sold this thing. And the techs would toggle in programs on that front panel. You see all those square buttons there? You could toggle in to the memory. The memory was actually on drum. It wasn't on core or anything like that. So the machine was really slow. It could execute maybe 1,000 instructions per second, maybe. But still, I mean, that was pretty cool. It had 1024 15-bit words. And as I watched them toggling in programs, they would mutter under their breath. You know, they would say they would punch in 15 in a certain number of bits and they would say store. They would punch in 10 in those same bits and they would say load. And I inferred what they were getting at. I had never seen a machine language before, but I inferred that these were instructions that they could put in memory, and then the instructions could be executed. And then by listening to them, I acquired a very minimal repertoire of instructions that I memorized. And then when they left, I would walk up to the machine and I would toggle in some silly little program and execute it. And I got lucky, because I didn't realize that you had to tell the programmer, you had to tell the computer to stop. But I always put a 0 at the end of my program because I needed the constant 0 to load that into registers. And it turns out that the constant 0 was the halt instruction. So I got a little bit lucky there. Otherwise, it would have just run away and never executed anything. These machines were actually built by a woman whose name is Judy Allen. She was a math teacher. And she got hired by the guy who had the original idea. And she literally wired these machines together, you know, in her, not her basement, in her living room and in a lab later on. And then she was the one who eventually wrote an assembler for this machine in 1024 15-bit words out of raw binary. So, I mean, you want to talk about a programmer? Okay. Writing a symbolic assembler in raw binary in 1024 15-bit words in a machine that uses drum memory and executes maybe 1,000 instructions a second. So just get that. Oh, by the way, she had to toggle that program in from the front panel. So this is where languages began. Now, they didn't stay there for long because everyone kind of realized that we better do something better than that. And so other languages were invented. And of course, the first languages were assembly languages, which were just machine language again, but with a slightly symbolic flavor to them. And instead of, you know, toggling in 15 for the store instruction, you wrote STO for store on a card somewhere. And you could name memory locations. You didn't have to do, you know, octal memory locations or hexadecimal memory locations. The assembler, if it was good enough, would do the address arithmetic for you. So it would take care of some of the low-level math that you needed to do to calculate addresses and so on. We would write our programs on these coding forms. You see that at the upper left there, that green sheet. We would write our code on that in pencil. Programmers in these days did not use keyboards. They didn't know how to type, right? They would write with pencil on these coding forms and then hand them to somebody else who would punch them on cards. You can see a punch card down there at the bottom. And the machine that did the punching was that key punch machine up to the upper right. That was I think that's an 026, IBM 026 key punch. That's the machine I learned to type on. You know, when I taught myself to type, it was on that machine there, deciding that I was going to type my own programs rather than give them to somebody else to screw up. Now we're moving in a kind of chronological order here, but I'm not going to be too close to chronological. I just kind of want to walk you through what was going on. By the time we get to the 60s, IBM dominated the space. They were the ones making computers, and they were big. I mean, look at this machine. This is a huge machine. No one could buy this machine, right? You had to rent it from IBM, and he rented it for tens of thousands of dollars a month. This was an expensive deal. These machines were multi-million-dollar machines. Notice the floor. You see that nice paneled floor down there? That's a raised floor. It was raised about 12 inches above the real floor, and it was below those panels that all the cables ran. You don't see any cables there, do you? That's because they're all below the floor, right? All computer rooms in those days had these raised floors to deal with the massive numbers of cables that were running around between all these really hefty units. The room was also environment controlled. You had to have a massive air conditioner in there because these machines, they put out a lot of heat. We're talking kilowatts here, you know. And you put that you put these things in a room without air conditioning, and the temperature goes up to 200 Celsius, and they don't work at that temperature. So here is a coding form with basic assembly language on it. This was the language that you programmed an IBM 360 in, that machine I just showed you. You can look at it here, and you can see that there's this kind of symbolic language. Some of you have probably programmed in assembly language before. Many of you have not. This is assembly language. And if you look at the right, you'll see there are comments there. Those comments were absolutely essential. No one could understand a program without comments in it. Can you imagine reading code that's nothing but those 2 columns or those 3 columns? It would be awful. And so we learned in the early days that comments were absolutely essential. That's a little trick that we didn't unlearn in time. By the time we got very expressive languages, we were still in the habit of writing horrendous comments, and the comments went from an absolute necessity to a liability. Something that we really didn't want in most cases. Sometimes you have to write a comment, but most times now, you're better off not writing it. I'll talk about that when I talk about the clean code course later on. But by 1953, we had a high-level language. Now, it's not very high level. This is Fortran in 1953. John Bacchus designed this language. But it was all the rage. You know, all the programmers were going, oh, Fortran, oh man, so this is so cool. I don't have to use assembly language anymore. You can see that we hadn't learned about indenting yet, right? It still looked like assembly language. We were so used to that column that we just continued to write it that way without any indentation. And in fact, there's hardly even the concept of a block, right? Now, if you look carefully, you will see that do statement there. See that do statement? And the next number over is the number 10. Look at the line that's got the 10 on the far left. That's the end of the do loop. So we did have blocks, sort of, but we didn't indent them. And people talked about indenting, but everybody else kind of wrinkled their nose up at the idea and said, well, why would we want to do that? We just want everything over at the left edge, because if we indent, then we have less lines, less space to put on our cards. And remember that in those days, the cards had only 80 columns. And the last 8 columns you couldn't use anyway. So you really only had 72. And Fortran actually took the first 6 for something else, you know, all those line numbers in there. So we really only had, like 60 some odd columns to put our code in. So indenting, we thought, well, that probably used up too much space. It didn't take long for languages to improve. This is an example of Algol here. This is Algol 60. And I put these two up here. One of them comes from a book. And notice that it's all lowercase and it's got italics and stuff like that. Even in the early 60s, right, people began to realize that they didn't want to see their code in just uppercase. So when they wrote books about it, they would put it in lowercase, and italics and bold to try and highlight the language. But when you actually saw a listing, it looked like that bottom down there. And even that one is adorned with underlines, which somebody actually drew on the listing because those underlines were not actually in the listing itself. We didn't have much in the way of fonts in those days. Like we had one font, and it was a mono font. It was whatever the IBM printer printed. And we really didn't have lowercase letters either. The key punch machine did not have lowercase letters. So if you were to look at a real listing of real code, it would have all been uppercase. And honestly, I could not find an example of Algol that did not come out of a book that somebody had messed around with. But this was Algol. And you'll notice a few interesting things about it. They do have the concept of blocks. See the begin and the end. That's kind of cool. And indenting had been invented by then, so that's kind of cool. Although they didn't seem to use the indenting rigorously at all. And they had one-liner if statements. And goto was the goto. That was what we used to transfer control. So you see there's plenty of gotos being used there. Now we're still in the early days here, and this lady here is Grace Hopper. Grace Hopper, what an interesting character. She's a lieutenant in the Navy. She learns about radar. There's data processing in radar, right? She learns about these electronic computational machines. She gets into that. Eventually, she becomes what today we would call the CTO of Sperry Rand, UNIVAC. Right? But in the early days, she was in the Navy, and eventually became an admiral and a commodore in the Navy. Pardon me. She looked at the languages that were in use and had a different vision. Her vision was that a computer language should be as close to a natural language as possible, so that non-programmers could read the program and understand it. The business people ought to be able to read the program and understand it. She wanted the program to be the functional specification, written in English in her case, so that non-programmers could read it. This, of course, was a disaster. It was, although ethically and morally, it was a lovely goal, the actual implementation was a disaster, which we now call COBOL. It was a disaster that was wildly popular for 30 years. A tremendous amount of code was written in this horrible, horrible language. And then eventually, finally, we did away with it. So there's very little COBOL being written today, and most of that is in maintenance mode. If you ever get a chance to write a little bit of COBOL, take the opportunity, but put some tinfoil around your head, because the demons will try to come in and ruin your brain. Right around the same time, BASIC was invented. Did you know that BASIC was invented in 1964? It was right around the same time. And it was invented by these two guys. Actually, it was invented by a team of people, most of them graduate students and pre-graduate students, right? And what happened here is that General Electric, who built massive computers at the time, donated a machine to their institution. And said, you guys ought to come up with a college curriculum for programming. Do you realize that there were no college courses for computer science at that time? Right? There was no way to learn how to be a programmer except to learn how to be a programmer on the job. Right? So there were no courses you could take. So GE said, hey guys, you should make some courses, and here, we'll give you a computer if you'll just make courses. And these guys sat down and they realized something important. They realized that there was no way that you could convince an 18-year-old to write their code on a coding form and have them hand it to somebody else to punch it and wait 24 hours for that deck to come back, and then hand it to an operator and get the operator to compile it at 3 in the morning and wait 24 hours for the turnaround of the compile. They weren't going to get 18-year-olds to do that. That's what everybody else was doing in the industry, but they knew they couldn't get 18-year-olds to do that. So these guys, in assembly language, wrote an entire new operating system. This operating system could handle multiple teletypes simultaneously. It was a real-time time-sharing system that they wrote, one of the first. And on top of that, they wrote a compiled language. It compiled right down to machine code, which they called BASIC. And they had to invent a way for students to edit their programs. And they came up with the brilliant idea of using line numbers. You type the line number and then you type the line. And if you don't like that line, you type that same line number again and you type the new line that you want. And if you want to insert a line, then you have to choose a number that is between two numbers. And that's, of course, why they increment their line numbers by 10. Why did they have to do that? Because there were no displays. The terminals were all teletypes. They were all printers. There was no way to scroll, right? You couldn't kind of, scroll up and down on the display. You could print your program out and it would look like what you see here on the screen. But that was a printout. And by the way, it printed out at 10 characters a second. So this thing here would take 10 minutes to print. So you were pretty careful about stuff like that in those days. But after 2 years of work in raw assembly language, they managed to get this operating system and this language working. And students were able to sit at a terminal and type a program in a matter of minutes, well, hours, and then execute it and see the results instantly. And this is the first fast turnaround anybody had seen. This actually became wildly popular, not just with students, but with everybody. And GE saw this as a business opportunity, and they planted these computers all over the United States and strung modem lines everywhere. And so the physical laboratories, the pharmaceutical laboratories, the weather labs, the physics labs, and even some companies would have these modem lines brought into a teletype where they were typing BASIC in the early 60s. But that, of course, didn't last because the computers were going to shrink. And they shrank to that. Now we're talking about the late 60s here, and you can see behind me, if you want to look at my picture, there's one of these PDP-8s sitting behind me, but they look like this. Now this is a machine with 12-bit words and 4K of core. You notice it's still got a teletype. That was the primary input and output device. But this machine sat on a table, and you could buy it for $15,000, in 1968 dollars, which, in now today's dollars, that would be about 150,000. But still, that was approachable. A real company, a small company, could look at that and think, I could buy that. All right, it's going to cost me 15 grand. That's a lot of money, but I could buy that and I could program things into it. So a lot of people started buying these machines. And what were they programmed in? Well, they were programmed in assembly language. They had a Fortran compiler. It wasn't worth using. Yeah, if you wrote Fortran code in this Fortran compiler, you could only have, I'm trying to remember the number, I think it was 13 forward references. If you jumped ahead to a line that was ahead of you, you could only have 13 forward references because they didn't have much memory, right? It was a 4K machine. Try to write a Fortran compiler in 4K 12-bit words. So most of the programming was done in assembler. And this is PDP-8 assembler that you're seeing there on the screen. That's a standard kind of, thing that you would do in PDP-8 assembler. Now, the year here is mid-60s, right? Late 60s. And what was going on in the late 60s? Well, these guys, this is Ola Johan Dahl and Christian Nygaard, and they're in Oslo, and they're working in Algol, that language I showed you before, Algol 60. And they're mucking around with this language. They're trying to write a simulator for navigating ships in and out of the fjords of Norway, because, you know, there's oil and they wanted to, you know, plot the best courses and stuff like that. And as they're doing that at the university there, they stumble across this idea, and I'm not going to go into the long and short of the idea. I'll just say, you know, they stumbled across this idea of moving the function stack frame to the heap and allow the function stack frame to persist longer than the function that created it, and objects were born. And they came up with the word class. You see it there, don't you? This is the language Simula, Simula 67, which is a minor dialect of Algol 60. And they added a few keywords like class, and they invented inheritance and polymorphism. They did all of that stuff and came up with what amounts to the very first object-oriented language. They did not coin the term object-oriented. That came later. But they did come up with this idea of classes and base classes and derivatives and so on. There were two people who were Simula programmers that will come into our story in a few minutes. But I want you to look at that code and see some of the similarities in modern computer languages. You know, the begin and the end, okay, that looks like Pascal, doesn't it? Class, that looks like Java, looks like C++. Look at the keyword virtual there. That's C++ and C#, isn't it, right? And oh, char for characters, isn't that interesting? So there's very interesting similarities beginning to creep in. Our languages are starting to become recognizable. But we're close to the end of the 60s here, and a remarkable thing happens in 1968. These two guys, Ken Thompson and Dennis Ritchie, right? They're working on a project called Multics, the multi-processing operating system that Bell Labs wanted. And they're not making any progress, and it's going badly. And they eventually get the project canceled underneath them. And they wind up with nothing to do, and they steal time on a PDP-7, I think it was, on a floor above them. And they, in the midst of that stolen time, they do two things. They write C and they write Unix. And they change the world. C, the language that changed everything. All of a sudden, this language came about. Now, it came about through a number of stages, right? These guys had started writing an assembly language, and they didn't like that, of course. So then they wrote a funny little language that was slightly more symbolic than assembly language, but was still pretty much assembly language. And that was called BCPL, Basic Computer Programming Language. Well, they didn't like that one so much. So then they added a few little widgets to it, and they called that B. I don't know why they called it B, but they called it B. And then Thompson and Ritchie go up to the floor, and they steal time on the PDP-7, and they make the obvious next language, right? C. B, then C. That's why it's called C. And they do a number of fascinating things. Now, I'm not going to go through all of the fascinating things they do, but this is the language that changed the world, and the operating system that changed the world as well. Modern languages, most modern languages, are direct derivatives of C. C++ certainly is, Java certainly is, C# certainly is, Ruby is, Python is. These have direct connections back to C. C had an inordinate effect on languages going forward. Now, there was a guy about this time. His name was Alan Kay. And Alan Kay was working at Tektronix. And he had a vision. And the vision he had was the iPad, literally. I mean, he thought that people would eventually be walking around with these skinny little screens that they could interact with. If you ever watched 2001 Space Odyssey, they had an example of that. The movie there shows the astronauts using what they called a news pad, and they would throw their news pad down and they could interact with it. Well, that was Alan Kay's vision. He thought that students in school and people everywhere would be able to interact somehow. He didn't really envision the internet, but interact somehow using these flat screen things. He called them Dynabooks. And He was a Simula 67 programmer, right? He'd learned object orientation by writing Simula. And somebody challenged him at one point to write a language, an object-oriented language, in a very short period of time. The legend is overnight. I don't know if it was really overnight, but he did. He came back very shortly with the language Smalltalk. And the language Smalltalk changed everything in a very narrow community. The rest of the programming community paid no attention to this at all, but a very narrow community looked at this and saw something very different from what they had begun to program in before. This was the early idea of an IDE, the early idea of an environment. Graphical user interfaces were part of this. The Tektronix was experimenting with those at the time. The notion that code was not carried in source files. we dropped that one. Although we might want to bring that back at some point. But a Smalltalk program is not written into source files. It's written into a database, the image. If any of you have ever programmed in Smalltalk, you know exactly what I'm discussing here. Smalltalk was, and I speak of it in the past tense because it is, for all intents and purposes, a dead language now. But Smalltalk was an extremely minimal syntax language. It had almost no syntax. And it was probably the most object-oriented language ever. At almost exactly the same time, you've got Jarne Stroustrup. Jarne Stroustrup was a Simula programmer, same as Alan Kay. And he got hired by Bell Labs, and Bell Labs was working in C at the time, and he couldn't countenance working in C. So he wrote a little simulator, a little preprocessor, not a simulator, a preprocessor in front of the C compiler. He called it C-front, in front of the C compiler, C-front, that would compile a new language, which he called C with classes, down into C. And he made C look like Simula. That was his point. He wanted to make C look like Simula so that he could continue to program in Simula. And that was in 1980. By the time 1983 came along, a whole bunch of people at Bell Labs were using this C with classes language. And one of them came to him and said, you know, you should change the name because C with classes is a terrible name. C++ would be a better name. And so he changed the name. Then in 1986, he wrote the book. Now, for this, I need to go back a little bit. Those of you who were C programmers in the long, dark past, you know what book you had to have, right? All C programmers had to have this book. It was the only book you had to have, and you had to know where it was at all times. You could never be more than 50 meters away from it. And this was, of course, the Kernahan and Ritchie book, the C programming language book, right? And we all knew that the table of operator precedence was on page 49, right? Because you had to look that up all the time. That book was an astounding book. It was written in an approachable way. It used lowercase to show the code, which most programmers were just over the moon about. It was very easy to read. It had a lot of code in it, and it had a chapter 0, right? And all the geeks go, yeah, chapter 0, yeah, okay. In 1986, Stroustrup writes the C++ programming language, same title with 2 pluses in it, uses the same font, same writing style, same book form factor, chapter 0, the whole thing. And all the C programmers look at that and go, oh, this is the next C. I don't think anything had a more profound effect on transitioning people away from C and towards C++ than that book. Anyway, he writes C++, and what you can see on your screen is a little bit of C++ code. And you look at that and you see, oh, yeah, that looks kind of like Java, doesn't it? Well, there's a reason that it looks like kind of like Java, because Java was a copy of C++, but we won't go into that too much. It still looks quite a bit like C as well, doesn't it? But you notice how the languages are shifting here. Now, Gosling comes along, and this is roughly 91, 92. And Sun Microsystems is in their heyday, right? They're making hardware, and people are buying their hardware. And one of the people who bought their hardware was a cable television company And they wanted to buy Spark stations to put on top of everybody's TV, and the cable signal would come into the Spark station, and then the video signal would come out of the Spark station. And the Spark station would put the TV guide up on the TV, and you could interact with it. And they wanted Sun to write that code, and Sun told Gosling to write that code, and Gosling had a team of programmers. And Sun had made a huge commitment to C++ by this time. C++ was their language. Well, Gosling didn't want to write C++. He thought it was a terrible language, so he wrote something that looked a little bit like C++. He called it Oak, and that's what he wrote that cable television set-top box thing in. And then sometime later, Sun Microsystems decided, and this is when the internet was starting to get really, hot, right? And Sun Microsystems decided they needed a language that would be the language of the internet, because what better way to convince programmers that you were making the right hardware if you handed them the language of the internet? So they looked around for the language of the internet, and here's Gosling with this Oak thing. And they thought, yeah, let's use that. But they didn't like the name Oak. So they figured, coffee, programmers like coffee. So they named it Java instead. That's where Java came from. It's just kind of a Chinese copy of C++, simplified and softened and made a little bit friendlier. Pretty much it. And then I won't even talk about C# because that's just Java, right? It's just plain old Java. Microsoft stole it and turned it into C#, but it's really just Java. And then in the 90s, you've got Ruby and Python. Now, this was a huge break. Up to this point, these languages had almost all been statically typed languages. C was actually not typed at all. And then C++ was statically typed, and Java was statically typed. But here come these languages like Ruby and Python, and they're dynamically typed. And how did they learn dynamic typing? Well, they learned that from Smalltalk, right? Ruby especially is an almost, Kent Beck once said that I knew Smalltalk would be resurrected, and it's been resurrected as Ruby, right? So you see these happening here, and here's the guys who invented these languages. By the way, do you notice that all these languages were invented by people, not companies, people, individuals typically, right? That's where most languages come from. They don't come from, some great conference of great minds. It's usually a guy, who comes up with some language and then somehow makes it popular. And then the standards bodies come in with the great minds and ruin the languages. So typically what happens. The story of languages continues. I don't want to belabor it much beyond this because we've got a lot of things we need to talk about. But I want you to look at the screen and just notice not how many languages are there. Notice how many languages aren't there. How many languages are missing, because I couldn't fit them on this slide. Why are there all these languages? What is going on? Why do we constantly come up with language after language after language after language? Now, I can make the argument that the transition from binary to assembly language was really significant. That helped a lot. And the transition from assembly language to Fortran, that helped a lot too. Not as much as the transition from binary to assembly language, but still helped a lot. And then the transition from Fortran to C, that helped a lot too. Not as much as the transition from assembly to Fortran, but it still helped a lot. And then the transition from C to C++, well, that helped a little. And it was better, not a lot, but a little. And the transition from C++ to Java, that helped a little bit, not a lot, just a little tiny bit. And then from Java to what? To Go. Okay, that's better. It's better. Is it remarkably better? Well, I mean, if you talk to a Go programmer, they'll tell you it's remarkably better. But in the grand scheme of things, it's a small incremental change. And that's what's been going on with our languages. Every new language is a small incremental improvement, and the size of those increments have been shrinking dramatically over the last 70 years. So that now these new languages come along and they have, okay, then, it's a little better. Okay, fine, whatever. But it's not like, whoa, a big difference. I wonder if we're coming to the end of that. Well, I'll talk more about that later, but I wonder if we aren't coming to the end of that. And of course, there is a language here that I skipped. I didn't mention. And of course, you know what that language was. It's Lisp. Lisp was invented way the heck back in time. 1957 is when John McCarthy wrote the first Lisp compiler, but the language itself actually has its roots in 1936, right? So it's a very, very old language. And this is the language that is still with us. It is the oldest language that is still with us. It refuses to die. We've tried to kill it. We've tried to kill it several times. It refuses to die. It's kind of like the cat that keeps coming back. And no matter what you do to this cat, it keeps coming back. Lisp is kind of like that. So keep that in mind as we switch gears. All right. Told you about languages, but something else was going on at the same time that all this language evolution was going on. And what was going on at the same time was paradigm evolution. And the word paradigm just means form or pattern. And we try to use that word to be, erudite, paradigm. But okay, it just means a pattern of coding in this case. We're going to spend a little bit of time walking through these paradigms. And I want you to watch as we do that. I want you to keep in mind what was happening to the languages at that time. And we begin way the heck back in 1936 with Alan Turing, of course, who wrote arguably the first programming language. Now, to be fair, you'd actually have to go back to Babbage for that. Babbage actually did have a programming language, or at least a machine language, for his analytical engine, although that was never implemented. And you could also go back to the guy's name is Zeus, I think, who had a little machine language in the 40s. But it was Turing who really gave it a mathematical basis with this lovely paper. And if you have never read this paper, I urge you to read it, but read it with a book. And the book is The Annotated Turing. That's the title of the book. And it's written by Charles Petzold. It's the greatest thing Charles Petzold ever wrote. It's a masterpiece, and it is a wonderful thing to read because he reproduces Turing's entire paper, and he quotes it almost sentence by sentence, surrounding it with all the history and explanation, and it's a fascinating book to read. I've read it twice. I'm going to read it a third time, and it will give you a profound insight into what was going on at the time and why we are where we are at the moment. At the same time, this guy, Alonzo Church, was making the lambda calculus for the same reason that Turing was making his Turing machine too, but they were trying to solve the same mathematical problem. And this lambda calculus, we all now recognize because we've all got lambdas in our languages. We had to put lambdas in everything. C++ has got lambdas, Java's got lambdas, C#'s got lambdas. These languages that should not have lambdas in them now because they're all really popular. But okay, this concept is old, very old. 1936 it comes from. The foundation of Lisp comes from lambda calculus and functional programming as defined by Alonzo Church. And of course, now I mention Lisp again, because John McCarthy wrote Lisp in 57, and it was an attempt at a functional language. And of course, they couldn't quite do it because the machines back then were way too primitive to allow them to do, real functional language, but they were approaching a functional idea in 1957. Now, functional is one of the paradigms we're going to talk about, but I'm going to leave it for the moment because we have to go somewhere else. We're going to go to structured programming in 1968. And by the way, this is the book. This book was published in 1972. If you can get a copy, you probably on eBay, you can find a copy. If you can get a copy, this is a fascinating book to read. In this book, you see the discussion where Dijkstra makes the argument that GoTo is probably not such a great idea. And in this book, you will see the argument by Ola Johan Dahl about objects. He doesn't call them objects, but he shows you the tells you the history of how they created Simula 67 and what the advantages were and so on. So fascinating book to read. If you ever get a chance to read it, I strongly encourage you to do so. But the structured paradigm and the object-oriented paradigm arose almost simultaneously at these times. Dijkstra in 68 writes the paper, right? Go to considered harmful, right? And he lays the foundation for the paradigm of structured programming. Ole Johan Dahl and Christian Nygaard in 66, before Dijkstra does the go-to paper, have already invented object-oriented programming in their Simula 67 language. And it wasn't that long after that that Alan Kay turned it into Smalltalk, which by a lot of argument is the real object-oriented language. These guys, Harold Abelson and Jay Sussman, wrote this book, The Structure and Interpretation of Computer Programs, in 1975. Notice it's not that long after all this change happened. And this shows the language Scheme, which is a Lisp variant, and is probably the first real functional language. And they wrote it to be a true functional language. Now, let's go through these paradigms. Dijkstra's paradigm was structured programming. And what was it all about? Well, Dijkstra, interesting dude, he gets exposed to computers in 1950 something, right after World War II, right? He survives the German invasion of the Netherlands. And then as a young man goes to college and he learns about computers and decides, I want to be a computer programmer. He makes this decision at a young age, but he is afraid that no one will take him seriously because there's no math behind it. There's no discipline. And his thesis advisor says to him, you know what? You might be one of the guys who comes up with that discipline, who comes up with the body of knowledge. And Dijkstra took that to heart and became one of the founders of computer science. Fascinating that he did all of this work on unreliable, slow, horrible machines with really terrible input-output rates, teletypes. What he was after was a mathematical foundation of software. He wanted to prove programs correct. And you may have seen documents where they actually tried to prove programs correct mathematically. He's the guy who invented that mechanism of how to prove programs correct. But he found that a program that has unconstrained go-tos cannot always be proven correct. Any program without unconstrained go-tos can be proven correct. There is a logical way to prove a program correct if it has no go-tos. But if it does have go-tos, you might not be able to prove it correct. And this goes back to the halting problem. And I'm not going to go through the mathematical derivation of it. But this is why Dijkstra said that go-to was considered harmful. And it was the advent of this style of programming, structured programming, which is a recursive algorithm of placing sequence, selection, and iteration in a time sequence. And every iteration can contain selections and other iterations and other sequences. It's this recursive application of sequence, selection, and iteration. That is structured programming. And you cannot have unconstrained go-tos in this kind of mindset. There's no way to jump, right? You can return from a loop, you can return from a function, you can split the flow of control in 2 or 3 or 4 ways, but you cannot just arbitrarily jump. And we call this, or I call this, discipline imposed upon direct transfer of control. That's really what structured programming was. It's not that you could not transfer control, because you can at the bottom of a loop or in the midst of a selection. It's just that there's a discipline imposed upon direct transfer of control. You can only transfer control directly in certain circumstances. Now, there was a huge war over this in the early 70s when these papers came out and Dijkstra's idea came out. And by the way, there was no internet in those days. We didn't have social networks. We did, however, have trade journals. And so the flame wars were fought in the letters to the editors. And they were just horrible, right? Dijkstra's an idiot. No, Dijkstra's a god. And this went on for about 5 years. And then the war was won. And Dijkstra won the war. And you can tell that Dijkstra won the war because modern languages do not have go-tos in them. Java, there's no go-to there. Right? I know you're going to complain about, breaks and continues and label. Those aren't go-tos. Those aren't go-tos, not in the sense that you can jump out of one function and into another. Right? And even languages that do have go-tos, we kind of started to frown on that. No go-tos, right? So the use of go-to waned away, and modern languages just don't have them at all. This iterative and recursive application of sequence selection and iteration forces us to decompose problems into functions, functional decomposition. And that drove us towards structured analysis and structured design. This was at the time when we were all in the thrall to waterfall and everything had to have 3 components: analysis, design, and implementation. And so we came up with these words, structured analysis and structured design, which again, emphasize this notion of the recursive application of sequence selection and iteration, all for the quest of provability, which failed horribly because we do not prove our applications correct. We don't do that. None of us do. We don't write the proofs that Dijkstra wanted written. Dijkstra wanted there to be a library of theorems, something like Euclid's Elements, and programmers would draw from those theorems and then write extra little lemmas on top of it. He wanted a mathematics. And that's not what we wound up with. What did we wind up with? We wound up with the opposite. What's the opposite of mathematics? Science. Science is the opposite of mathematics. Why? Because in mathematics, you prove from basic principles. And in science, you prove nothing. You observe from the end result and then try to extrapolate down to principles. Nothing in science can be proven. Everything in science must be tested by experiment. And if those experiments reproduce the same results over and over, you can sort of say, well, maybe that's a rule. But you're always tentative about that because some experiment somewhere is going to violate that rule. Right? So you never prove anything in science. You prove things in math. You don't prove in science. And that's what we do in software. We don't prove anything. We test. We test. And so software is more like a science than a math. Although the logic that provability is important is still there. Because you cannot derive to basic principles if you cannot work through a chain of reasoning. So if you've got a program that cannot be proven correct, it means you cannot reason about it. And therefore, we still follow structured programming, even though we test things scientifically, as opposed to anything else. And I'm going to skip over the rest of these slides because I think I've made that point. That was the structured paradigm. Discipline imposed upon direct transfer of control. Now, when was this happening? This was happening in the middle of the 60s, right about the time that C and Unix and Pascal and these languages were being created. So fascinating what was going on at the time. We'd already gone through Fortran and Algol, and now we were into these languages that formed the core of everything we do today, C, right? So fascinating what's going on. Not only is there a change in language, but there's this change in mindset. Object-oriented programming, what the heck is that? Well, what is OO? Now, this is a question that has been bothering people for quite a long time now. What the devil is it? And many people will say, well, it's just the combination of data and function. And my response to that is, well, are you sure? Is O.F really superior to F of O? I mean, does it matter that the F is inside the class or outside the class? It doesn't really, does it? I can write the same program with data structures and functions that I could write with classes. So there's no real difference there except for a bizarre syntactical thing. Some other people say, well, no, you don't understand. OO is the strategy of modeling modeling the real world? And my answer to that is, no, it's not. It's a mechanism for writing software, and software doesn't have an awful lot to do with the real world in any case. And even if it did, the models we built in C before there was OO were just as good as the models we built in object-oriented, because again, it doesn't really matter if you write the functions outside the class or inside the class. So I'm not going to go for this modeling the real world thing. And then other people will just get mechanical, and they'll say, well, OO is really just about encapsulation, inheritance, and polymorphism. And okay, that seems like a tangible definition: encapsulation, inheritance, and polymorphism. But I gotta tell you, we had much better encapsulation when we were programming in C. When we were programming in C, we had header files and implementation files. And we didn't have to put any implementation at all in those header files. In C, there was no implementation in header files at all. And so we could completely separate implementation from interface in C. We could keep things perfectly encapsulated. But then along comes C++, right? And C++ breaks encapsulation. Why does it break encapsulation? Well, for a technical reason, Strustrip needed to know the size of the object in order to write the new keyword, because he had to allocate memory, so he needed to know the size, and that meant the header file had to have the implementation in it, which of course violated capsulation. And then to try and kind of recover that capsulation, Strustrip put these horrible hacks in, public and private, and then eventually protected. All those terrible encapsulation keywords got stuck in the language. We were much better off with C, much better off with C. We could encapsulate with C. In C++, encapsulation was broken, and we tried to kind of fudge it back with these horrible keywords. And the problem with the horrible keywords is they don't actually solve the problem. They impose restrictions in what you can access, but the compiler still knows about that implementation. If I change the type of a variable in a header file, I still have to recompile all the .c files, all the .cc files. So the dependencies are still there, even though the access is restricted. It didn't really help very much. So I'm not going to award OO any points at all for encapsulation. We had encapsulation before OO. Eventually, Java and C# just gave up with the whole header file split, right? Well, we don't need to separate interface from implementation because there's no point in an object-oriented language. We have to combine them anyway. So Java and C# just gave up and mixed interface and implementation together. And then, of course, they came up with the notion of interface classes, which sort of helps, but not as much as just regular old encapsulation in C. What about inheritance? Did we have inheritance in C? And we did not, of course. And the reason we didn't have inheritance in C is that it was just so easy to fake. I mean, nobody even thought about inheritance. We just kind of made data structures that were real similar to each other and created pointers that could be aliased to different data structures. So it turns out that in C, you could have single inheritance very, very easily. Now, okay, it was a little bit of a convention and you had to follow the convention, but it wasn't an onerous convention. So we did it all the time. It was just standard C programming to have a bunch of data structures that were fairly similar in one data structure that held all the common elements, and we would use pointers to that common data structure and then cast them if we had to. It was a very common kind of approach. So, okay, you can kind of say that OO gave us inheritance, and I'll give you half marks for that because it did make it a little more convenient, but not much more convenient. So, okay, you know, you get negative points for encapsulation because OO wrecked encapsulation. You get positive, maybe half point for inheritance, but not much. I mean, it wasn't a great advantage, but where we really get the advantage of OO is in polymorphism. And that's a perfect time for a break. It is right at the top of the hour. Let's take a 10-minute break, 10 minutes. We're going to start at 11 minutes after. All right, so do what you have to do, and I will see you in about 10 minutes.
Okay, many of you are asking about tours of these posters. So I'm going to show them to you. All right, let's see. So, all right. That one's about losing. If at first you don't succeed, failure may be your style. There, I don't know if you can see that one. Well, it's hard to see that one. You'll always miss 100% of the shots you don't take. And statistically speaking, 99% of the shots you do.
Here's my favorite.
Oh,
Idiocy. Do this one.
one right behind his head. Idiocy. Never underestimate the power of stupid people in large groups. And they're jumping out of a plane. Ineptitude. If you can't learn to do something well, learn to enjoy doing it poorly. Let's see. Mistakes. It's a sunken ship. It could be that the purpose of your life is only to serve as a warning to others. Mediocrity. It takes a lot less time and most people won't notice the difference until it's too late. So there you go. That's a couple of the the posters that are in the office. They're just fun. When you create something idiot-proof, the universe invents a better idiot. Nice. Nice.
Uh-huh.
Yes, the posters are from despair.com.
Yes.
Yep.
Mm-hmm. Yep. Most of those I bought 20 years ago.
Yeah, 20 years. We have about 1 minute left. No, Dilbert is in the other room, actually. He's hanging on the desk. Fools are too clever. That's funny. All right, I'm going to mute myself again.
I am now unmuted, and now I need to share my screen back. Let's see, where was I? Here, probably. Yep, good. All right, so I believe we are now back. So OO didn't really give us much encapsulation, although encapsulation is a part of OO. OO languages didn't help encapsulation, and in fact, for the most part, they hampered encapsulation, especially in strongly typed languages, statically typed languages. And inheritance, well, OO languages did give us the language facility to do what was actually pretty easy to do anyway. Until you get into multiple inheritance. It's hard to do multiple inheritance, but then again, most of our languages don't do that anyway, so who cares? What OO did give us was safe, easy polymorphism. Now, did we have polymorphism before? And the answer to that is yes. And if you look on your screen, you'll see the copy program there. The copy program, which calls get char and put char. And if you think about that carefully, you'll realize that that is a polymorphic program because this program does not know what devices it's using. Right? Get char just reads from standard input, whatever the hell standard input happens to be. Put char just reads from standard out or writes to standard output, whatever standard output happens to be. So this is pretty clearly a polymorphic program. Now, ask yourself how it works. How does it work that get char actually manages to get into the keyboard driver, for example? And the answer to that is buried deep down inside of Unix. The Unix IO drivers all had to conform to a certain function signature. They all had to have 5 functions, open, close, read, write, seek. And the signatures of those functions had to be identical. And if you think very carefully about that, you'll realize that that is essentially a Java interface or a C++ abstract class, right? It's the same 5 functions with the same exact signatures. And this is the key to it, The IO driver had a data structure within it that contained pointers to the functions that corresponded to those 5, right? So the read function for the keyboard driver would read from the keyboard. And the data structure would hold a pointer to the read function. That data structure with 5 function pointers in it would be copied into the data structure that the copy program was using. So getchar would look at this data structure and say, well, I need to call the read function. And it would find a function pointer in there, and it would call whatever function that was. And if standard in happened to be the keyboard, it would call the keyboard's read function. Now, those of you who have been C++ programmers know what that table of function pointers is. That's a V table. Those of you who are Java and C# programmers have probably never paid much attention to how that's done, but it's done in a very similar way. There is some kind of vector table of pointers to functions, right? Those of you who have never used an object-oriented language still understand this mechanism because we have callbacks, and it's the same idea. You just load the callback register with a pointer to the function that you want to call back. That's how polymorphism, for the most part, is implemented. There are other strategies, but that's the primary mechanism. Did we do this in C? Well, as you can see, we did, but it was really dangerous. When you've got a table of pointers to functions, someone has to be responsible for initializing that table, and everyone who calls those functions must call through the table. And that's an extremely difficult convention to enforce. One programmer off in Timbuktu violates that convention and all hell breaks loose. So the advice was, don't use pointers to functions. And that was written in all the advice manuals in the early days of C. Don't use pointers to functions unless you've got a really good reason. Don't use them. And we didn't use pointers to functions because they were dangerous. C++ came along and gave us safe, simple polymorphism. All of the management of the table was subsumed by the compiler. When you called the function, you did call it to the function pointers because that's what the compiler did. So all that convention got buried into the language, and suddenly polymorphism became safe and easy. Now, why is that important? Well, that's important for a really interesting reason. Yeah, I'm trying to get to the slide. First of all, it's important because we'd like to have polymorphism. Look at this code right here. This code is independent of a horrible detail, the device. If I have polymorphism, I can write code that is independent of detail. It has no dependency on the detail at all. It knows nothing about the detail. It doesn't know what device we're using. And in fact, the device we're using might not even be invented yet. I mean, this code would not have to be recompiled if I added a new device driver to Unix. It would still continue to work. So the power of polymorphism looks like this. What you're looking at now is the way every program prior to 00 was structured. Almost without exception. There were a few exceptions, but we won't go into those. And the structure is very simple. There's a main program that calls down to high-level modules, and there's high-level modules called to medium-level modules, and medium-level modules call down to low-level modules. And you see those green arrows, those green dotted arrows? Those are the calls. That's the flow of control at runtime. Now look at the red arrows. The red arrows are the source code dependencies. And what is a source code dependency? It's a pound include, an import, a using, a require. It is some statement in the upper module that mentions the name of the lower module. Main, pound includes HL1. HL1 imports ML1. ML1 uses LL1. There is a statement in the upper module that mentions the name of the file that contains the lower level module. That's a source code dependency. And notice that the source code dependencies and the runtime dependencies all point in exactly the same direction. Now, that's deeply constraining. It means that your flow of control dictates what the source code dependencies must be. But the source code dependencies dictate who gets compiled and when, and who must be there and when. Right? That's a bit of a problem for us. What happens with OO? OO breaks this entirely, because in OO, using an object-oriented languages, HL1 can call a function in ML1 without a source code dependency on ML1. See that interface in the middle there, that I interface in the middle? That declares the function F. And yes, HL1 does depend on the interface, but that dependency doesn't go any farther. And ML1, the function being called, depends on the interface. The source code dependency points in the opposite direction of the flow of control. This is called dependency inversion. The dependencies get inverted. And because of this, because it is possible, we have an immense amount of power, because this diagram can now be inverted. You can take any one of those red arrows you want and turn them completely around. You have now, with OO, you have absolute control over the direction of every single source code dependency in your system. Any of them you want to turn around, you can turn around. And that lets you do things like this. I can have the business rules utterly independent of the UI and the database and the framework and any other thing I want to make it independent of. I can turn those red arrows around, right? The business rules call the UI, the business rules invoke the database, but the database module depends on the business rules. The UI module depends on the business rules, because I can turn those dependencies around. And what does that mean? It means that things like the UI and things like the database can be plugins to the business rules. Plugins to the business rules. And I want you to think very, very carefully about that. All of the details in your system could be plugins to the high-level policy of your system. And knowing that, why wouldn't you design it that way? Why wouldn't that be your architecture? This is the power of OO. The power that OO grants us is this ability to have absolute control over the architecture of our systems. So what is OO? Well, okay, I mean, yeah, there's encapsulation in it, and yeah, there's inheritance in it, but that's all minor stuff. And in fact, the encapsulation is actually negative. The real power is in that polymorphism, and that polymorphism was based upon pointers to functions, but pointers to functions upon which discipline has been imposed. We impose discipline on pointers to functions, discipline on indirect transfer of control. And that leads us to functional programming. And what is functional programming? Well, functional programming is the act of programming without assignment statements. Now, that'll get a lot of people upset because I didn't mention first-class functions. Yeah. First-class functions automatically fall out if you say you can't use assignment. If you say assignment is out of bounds, you must have first-class functions. You simply have to. There's no other way to program anything. So the first rule of functional programming is no assignment. And I can demonstrate this pretty straightforward. Here's a little application written in Java, squares of integers. And if you're a Java programmer, you look at that and it looks perfectly normal, right? Public static void main. For int I equals 0, I less than 25, I plus plus, print the square of I. Perfectly normal, right? Prints the squares of integers. But now look at this in a functional language, that closure code in the middle there, that's the functional language. And if you're not used to closure, don't worry about it. It's not hard to learn closure. But you have to read it backwards. You can't read it in front ways. Or if you do read it front ways, you have to understand what's going on. So I'm gonna tell it to you backwards. See that range thing down at the end? It's in parentheses. Anything in parentheses is a function call, right? So I'm calling the range function there. And the range function simply returns an infinite list of integers. And yes, I do mean an infinite list of integers. It's returning an infinite list of integers. And right now you're going, well, how can you return an infinite list? Well, there's a clever little way, and I'll tell you what that is in a minute. Now, to the left, the next thing in parentheses is the map function, which takes the list you're passing into it from range and applies that star XX thing to it, which is just multiplying x times x. So it takes the square of every one of the integers in the infinite list of integers that I'm passing in. So this map function now returns an infinite list of the squares of all the integers. And then the next thing in parentheses is the take function, and the argument to take is the number of elements to take. So we're going to take the first 25 elements from the infinite list of squares, and then we're going to print that. That's the last thing in parentheses. So now we can read it forwards. Print the first 25 squares of integers. That's the way you would phrase this. And I want you to notice, first of all, that there's no assignment in there. There's no assignment operation going on. I'm not assigning anything, whereas in the Java program, I was assigning I. The variable I was changing state, but in the functional program, no variable is changing state. And I'm not going to get deep into this, but that's really what's happening. Now, by the way, how do they get the infinite array, infinite lists? They use iterators, right? So what's being passed out of there is not actually a list. It's an iterator, but it doesn't matter. It still looks like a list to us. We still treat it like a list. It's really just an iterator. So in the end, we never actually get more than the first 25 integers. Little clever stuff going on there. Now, again, this is not a tutorial on functional programming. I'm just trying to give you a little smell for it. And yeah, I did that already. So I'm just going to make the point now. Functional programming is programming without mutable variables. No variable changes state in a functional program. And if you argue with me that you can't write programs like that, well, then I'll show you a few that have been, right? And by the way, go back to that book that I mentioned earlier, the Structure and Interpretation of Computer Programs, that book. Structure and Interpretation of Computer Programs, SICP. Just do a Google for that. And by the way, the book is free. The PDF is free. You can just download it. And you will find an immense number of programs, very complicated programs, written that change no variables, whatever. It floored me when I first read that book. I was really quite astounded by it. So, without belaboring the point any further, the three paradigms, all of which were uncovered in the years between 1957 and 1968, so a very productive decade, were structured programming, object-oriented programming, and functional programming. There has been no paradigm discovered since then, nothing with anywhere near the kind of impact since 1968. Like you might look back on software and think, well, a lot of stuff has happened in software in the last 20 years. No, not very much has happened in software in the last 20 years, especially not at the language level, not at the technology level. Right? This stuff did happen. And what are these three paradigms? Structured programming, discipline imposed upon direct transfer of control, object-oriented programming, discipline imposed upon indirect transfer of control, functional programming, discipline imposed upon assignment or mutability. And notice that all three of those are negative. All three of those take something away that we had before. We used to be able to use goto. Can't use goto anymore. We used to be able to use pointers to functions. Can't use pointer to functions anymore. We used to assign things all over the place. Can't assign things anymore. Is there anything left to take away? Could we afford another paradigm? I mean, what would they take? I don't even want to think about that. What we learned in that critical decade from 1957 to 1968 was what not to do. Not what to do, what not to do. And those were the three paradigms that infected our languages. Structured programming infected our languages almost immediately. Object-oriented programming took another decade to start infecting our languages and really didn't hit the peak until around the year 95, when Java was created, and C# followed shortly thereafter. And then all the Rubies and Pythons and all that stuff started happening. All these object-oriented languages started happening in the late 90s, right? And then carried through into the 2000s and the 2010s. And then functional programming started to peak up about 10 years ago now, right? In around 2010. Nowadays, the best languages out there use all three paradigms, which means that they're the most constrained languages because they don't allow you to do go-tos, pointers to functions, and assignments. Now, are you using a language that doesn't allow assignments? Some of you are probably using a functional language or a so-called functional language, like maybe Scala, but Scala lets you do assignments. And you might be using F#, but F# lets you do assignments. There's a lot of languages out there that claim to be functional because they have a few functionally kinds of things in them. They're not actually functional languages because they let you do assignments. Closure does not let you do assignments. There are ways, but with discipline imposed upon them. And I'm not going to get into the depth of those ways. I just kind of wanted to give you a feeling for that. Now, here's an unwelcome fact. Software is not a rapidly advancing technology. The rules of software are the same as they were in 1946. The tools and the hardware have changed like crazy. I mean, holy cow. We've got IDEs, we've got machines that are blindingly fast. You know, we really have a very powerful bunch of hardware. And the hardware has allowed us to write very powerful software, but the software itself has not changed. It's still a recursive application of sequence, selection, and iteration, broken up into modules that are polymorphic in nature so that their dependencies can be controlled. And if we are wise, the data that flows through those modules is immutable. Structured, OO, and functional. That's where we are. And we've been there for a pretty long time, to one extent or another. And a lot of people still use assignment operators. So I want to put all this together now. I want to put this together into a synthesis. We've talked about languages, we've talked about paradigms. Future programming. Well, paradigms are not mutually exclusive. I want to make this point very clear. There's quite a bit of chatter out there on the net that says, oh, I'm a functional programmer now, not an OO programmer anymore. OO is terrible. Functional is great. Yay, functional. This is nonsensical, right? OO and functional are not mutually exclusive. They coexist, and they should coexist. Your software will be better if you use polymorphic dispatch and dependency inversion along with immutability. Structured programming is not the opposite of object-oriented programming because every one of your methods is going to be a recursive application of sequence, selection, and iteration. A good program is a recursive application of sequence, selection, and iteration, structured programming, tied together through dependency inversion, object-oriented programming, and piped through it are immutable data structures, functional programming. All right, so our future language, now we get to look into the future, right? Our future language has a first constraint. It must support all three paradigms concurrently. If we're going to do good code, if we're going to do good programs, whatever our future language is, it must support, must even enforce all three paradigms concurrently. There are very few languages today that do that, but some do. We'll talk about that later. Now let's talk about types. Some of you may have noticed that I didn't talk about types before. Let's talk about types now, and in particular, the great typing divide. Should we use static type languages or should we use dynamically typed languages? The history of this is kind of remarkable. It goes way the heck back into the late 1800s during mathematical struggles trying to come up with a a postulate-oriented derivation of all of mathematics. And I'm not going to go through that horrible scenario where people kind of lost their whole life's work in the last day of publication. I don't want to go through that. This is kind of a sad story. Suffice it to say that types were invented for mathematical reasons. Turing, when he did his Turing machine in 1936, was not thinking about types, but Alonzo Church was when he did the predicate calculus. And he was thinking about it because he knew of the mathematical derivation. The first language to really impose a type was probably Fortran. Fortran was a statically typed language. Any variable that began with the letters I through N was an integer, and every other variable was a real number, a floating point number. And you had to, if you did not declare them, that was the rule. Otherwise, you could declare them. Functions could not be called with types that did not match what their declared types were. So Fortran actually enforced sort of static type checking. Assembler? No, there's no static type checking. There's no type checking at all in assembler. You do whatever you want, right? And there really aren't even any types. There's just a machine word. C? C had types, but the compiler didn't check them. So you could declare a variable to be an int. You could declare a variable to be a double, but then you could pass a double into a function that took an int. The compiler would say, okay. And when you called it, it would pass it, it would push a double up on the stack, and then the function, when it ran, would pop an int, and it wouldn't be right. So we had some trouble in the early days with C because of that. And along comes C++, and that's got static typing, real static typing. It checks things at compile time, and we were so thankful. Thank you, Yarna, for giving us static typing. And the static typing went all the way into Java and C#, and it continues to this day, and into Swift and into Go and all these languages that are statically typed. Okay. But there were other languages that were dynamically typed. Lisp was always dynamically typed. So was Logo. That was just a variation on Lisp. Smalltalk was dynamically typed. Ruby, Python, all these languages were dynamically typed. And a dynamically typed language is still typed, but the type checking occurs at runtime, not at compile time. The compiler does no type checking, which means that in general, you don't have to declare your types. You just check them at runtime. And a lot of people are scared of that. In fact, there was a war fought over this. The war was roughly 1999. And the war was actually between two companies. And the two companies were Sun Microsystems and IBM. The internet was a thing by this time. Everybody knew that the internet was going to be really, really important. In fact, this was right at the height of the dot-com bubble, right? And Sun Microsystems had staked out their claim with Java and Spark stations. That was going to be the power behind the internet, Java and Spark stations. But IBM, a powerful force indeed, had decided that no, the internet was going to be their machines, whatever those were, those IBM machines, whatever they were, and Smalltalk. They had made the decision to use Smalltalk. Some of you may remember Visual Age for Smalltalk, that IDE that came out in like 1999. Some of you may remember that. This was the big war. IBM was bound and determined to push Smalltalk into the industry, dynamically typed language. Sun Microsystems was bound and determined to push Java into the industry, and they fought it out. But very interestingly, the soldiers in that war were not Java programmers, because there weren't that many of them in 1999. They were C++ programmers. The C++ programmers, who all knew they would be becoming Java programmers at this point, wanted static typing. And they fought a huge war over this. Now, what were the battles? The battle was fascinating. There was a study done by Capers-Jones about a decade before, maybe 5 years before. And this study showed that Smalltalk programmers, given a problem, were 5 times faster at delivering a solution than C++ programmers. 5 times. you know, and you know, all the C++ programmers go, oh, that's because our code is safer. And the Smalltalk programmers are going, we don't care, man. We're 5 times faster than you guys. That was the nature of the war. The C++ programmers won that war. They won the public opinion of that war. I mean, it's kind of weird to think about that, right? Because the Smalltalk programmers were provably faster. And yet the C++ programmers won that war. IBM had to shut down their whole Smalltalk effort, right? Smalltalk died as a language because of this, right? And the Java programmers, you know, walked away, you know, we're the C++, we're the winners of that war. Never forget that the industry had an opportunity to go 5 times faster and decided against it for reasons of quality. I don't want to hear, you know, how, well, you know, I've got to go fast because my business doesn't care about quality. The entire industry decided to go 5 times slower to preserve quality. Now, by the way, there was a lot more going on in that story than I just told you. The guys who were doing Smalltalk were badly crushed. They were very demotivated. Many of them went on to become Java programmers because what else could you do? So a huge number of Smalltalk programmers became Java programmers. But they took a discipline with them, a discipline that had been invented in the Smalltalk community for obvious reasons. That discipline we now call test-driven development. And they moved that test-driven development discipline into the Smalltalk, into the Java community, where it took hold and started to spread. And a whole bunch of Java programmers, a few years later, started looking around and going, wait a minute, we're writing tests. We know our types are good. Why do we need to be going 5 times slower with this statically typed language? They all became Ruby programmers. Right? That's where the Ruby thing happened. Rails came out right about that time, and they all just hopped over and became Ruby programmers. And there was a big demand for Ruby programmers in those days. The Smalltalk programmers eventually got their revenge. They plotted it very carefully, and they executed it flawlessly. What better way to take down the company that invented Java than to give their language away for free? And that strategy was called Eclipse, to blot out the sun. Anyway, you might find that to be an interesting history to study. In any case, the war was won. Static typing became de rigueur and stayed for a while until all the Ruby programmers started going around, and then people started doing Python. And nowadays, there's more Python done than Ruby. Python is the much more popular language than Ruby. But Ruby had a real spike in popularity for a while, and now Python has overtaken it, and Ruby has kind of collapsed because the whole Rails thing kind of fell apart in the end. This is the great pendulum of typing. This is a pendulum I've actually lived through about 3 or 4 times, right? Where the languages are statically typed, and then we suddenly want to do dynamic typed languages, and then we suddenly want to do statically typed languages, and then we suddenly want to do dynamically typed languages. And what you notice right now is that there is a move back towards statically typed languages after the whole big Ruby Python influx, right? Everybody was doing Ruby and Python, and then, oh gosh, it's really hard to deal with these types. We need type safety, and then they go back and they invent languages like Swift, right? So and Kotlin, which are very strong statically typed languages. They've gone the other direction. The pendulum has swung again. But static typing brings with it a dilemma, and it's an architectural dilemma, and it's a significant architectural dilemma. And I can demonstrate that dilemma this way. This is the typical abstract factory scenario. If you're familiar with design patterns, you know the abstract factory design pattern. We have an application up at the upper left which uses some kind of service. And because we want to do good architecture, we want to decouple the details of that service from the application. So we use a little polymorphism, right? So the concrete implementation implements the service interface. And of course, the application needs to create instances of the service, and it's not allowed to know about the service. And so it uses another little bit of polymorphism to create a factory. And notice that red line. See that red line? That's the boundary, the architectural boundary. And all the implementation is below the red line, and all the abstract high-level policy is above the red line, and all dependencies point crossing the red line towards the policy. That's the architectural dependency rule. All dependencies, all source code dependencies, point across the boundary, pointing towards high-level policy, from low-level to high-level. Now you look at that diagram and you think, well, that's great, but what would happen if you had two concrete implementations? What if it was really polymorphic? What if there were two different ways to implement this, and the application needed to choose between those two different ways? And you say, well, okay, if you want to do that, then you have to add another make function to the service factory. Ooh, but that violates the rule, doesn't it? If I add another make function to the service factory, you know, like make service 1 and make service 2, I'm changing something above the red line. I'm not supposed to change anything above the red line. I'm supposed to be able to implement things below the red line that don't change anything above the red line. And this changes something above the red line. And I can fix that by making that function make service in the implementation, in the interface there, take an argument, like a string. And half of you are going, no, make it take an enum, make it take an enum. No, I can't make it take an enum, because the enum would have to be defined above the red line, wouldn't it? And so it would have to change if I added a new type, wouldn't it? No, it can't be an enum, can it? No, it's going to have to be something opaque, like a string. And now half of you, sphincter muscles are tightening. You're going, oh my God, that violates type safety. Yes, this is a fundamental law of architectural physics. If you want to decouple interface from implementation throughout the system, there will be a place somewhere across the boundary where you must violate type safety. Type safety will force you to violate the dependency rule. If you want to enforce type safety throughout, you will violate the dependency rule. You will have some high-level policy depending on a detail that you don't want to depend upon. And therefore, the only way to get an architecturally sound system is to violate type safety somewhere. It doesn't have to be everywhere, but it's got to be somewhere. And once you face that, you begin to realize that maybe this type safety stuff comes with a cost, more than just a cost of 5 times the implementation effort, a real architectural cost. And if you are doing test-driven development, why do you need it? Why do you need static type safety if you're doing test-driven development? Because your tests are checking all the types, right? That's where the crux comes in for me. For me, I want my systems to be architecturally sound. Now, I still believe in type checking. I just want to check at runtime, not at compile time. I don't want the compiler forcing me into strict typing structures. I want to have the flexibility in my typing structures that are dealt with by tests. That's what I want. And I want at runtime a very sophisticated type checking system. This, by the way, is an example of a very sophisticated dynamic type checking system that happens to exist in the language Clojure. It's called Clojure Spec. And it allows me to declare the structure of my data very precisely and then enforce it at runtime. And it's very, very useful, and I find it to be almost invaluable. And I bury the checks inside precondition and postcondition checks in my functions, which you can do in Clojure pretty easily. And in my unit tests, I will have my unit tests call the type checking functions that will go through these very, very formally declared, much more formally than a compiler could declare them, except maybe Haskell. which gives you a tremendous power to enforce type safety at runtime. So this is my second constraint for a future language. I want future languages to be dynamically typed, not statically typed, but with sophisticated runtime type checking facilities. I want them to be dynamically typed because I want to go fast. I want that 5 times improvement. I also want to be able to build architecturally sound structures that do not violate the dependency rule. And I want very powerful type checking at runtime. So that's the second constraint that I want for a future language. Now, there is yet another issue, and it's the grammar divide. The great grammar divide. C++ is a grammar-heavy language. There's lots of little widgets and syntaxes and gestures and things that you can do, and you become a language lawyer. If you've ever read the C++ specification, it's big and it's written in a legalistic kind of sense, right? And we called people who are experts language lawyers. So you really, it's a really complicated language. Java is not as complicated, but boy, after they added generics, it got a lot more complicated. And then they added lambdas, and that made it even a lot more complicated. Oh God, it's starting to become a pretty syntax-heavy, grammar-heavy language. The grammar-heavy languages are languages like C, C++, Java, C#, Go, Swift, Scala, F#, Haskell. Ruby and Python, to a certain extent, are pretty grammar heavy. There's a lot of things you can do in Ruby and Python that are not, not outside of the language, they're inside of the language. Pascal and Delphi, very heavy grammar languages. Even Fortran was a grammar heavy language. COBOL was really grammar heavy. PL1 was really grammar heavy. So was Algol. And to some extent, BASIC was grammar heavy. These are languages that have very complex syntaxes and grammar. But there are other languages that have almost no grammar at all. Has anybody programmed in Forth? Forth has virtually no grammar. The grammar of Forth you could write in a half a page, maybe less than half a page. I mean, really, really light. Smalltalk has a very light grammar, almost no gestures in the grammar, because it's all taken care of by the browser, right? But it's the syntax for Smalltalk, again, you could probably put it on an index card. Lisp has almost no syntax at all. I mean, it's so devoid of grammar that people complain about it, because they complain there's too many parentheses, right? The syntax of Lisp is really light. And I can show you the syntax of Lisp here. What you see there is a Java call, f of x, right, with the semicolon there. And then in Lisp, that just turns into parentheses around f and x. And by the way, now you know Lisp, because that's about it. That's about the grammar right there. Because everything in Lisp is done with function calls. So that's pretty much the grammar of Lisp. If you're using Clojure, there's a little bit of extra grammar, not a lot more. But again, you could probably write the grammar of Lisp probably in 2 sentences. And the grammar of Clojure would probably take you an index card. And you might have to write small on that index card. But it's still a very light language. Now, what are the advantages and disadvantages? This gets interesting. On the left, we have heavy languages. On the right, we have light languages. Features are added to heavy languages by adding more syntax and grammar. And we have seen this, haven't we? We've seen it in Java, we've seen it in C++, we've seen it in C#. New and extra syntaxes, angle brackets and pound signs and other horrible things that you can put in the language to try and give it the gestures it needs for new languages, for new features. But in a light syntax language, these capabilities are added by libraries, by calling functions. And you might think that's a disadvantage, but I'll show you later why it's not. Heavy languages have strong compile time consistency. And what that means is that you have to work very hard to get every symbol just right. And the semicolons have to be. Has anybody ever compiled a C++ program and had the compiler yell at you by asking you, did you forget a semicolon? Heavy languages, you must be consistent. You must put a lot of effort into this consistency. Light languages don't require a lot of effort to be consistent. I mean, mostly you just have to balance the parentheses in Lisp. I mean, there's hardly anything to be consistent with. Heavy languages have a long grammar learning curve. It takes a long time to internalize all those rules. Light languages have almost no learning curve as far as the grammar is concerned. Library learning curve, yes. Grammar learning curve, almost none. Heavy languages have many landmarks. If you're looking at the code, you can see the landmarks. You can see where the classes begin. You can see the public and the private and the static statement. You can see the colons. You can see all these landmarks. That helps you read the code. People complain about light languages because there aren't a lot of landmarks in them, and that's true. It's definitely a help to have landmarks in your language. It is hard in a heavy language to make a domain-specific language within that language. Now, one of the goals of a good architect is to turn the high-level policy of your system into a domain-specific language that captures the business rules. And in a heavy grammar language, the grammar of the language overwhelms the domain-specific language you're trying to create. That is not necessarily true in a light language. In a language with light syntax, the domain-specific language you create as part of the architecture can outweigh, become more visible than the syntax of the language because there's hardly any syntax to the language. And finally, and this is really, really important, and it's not at all intuitive, heavy languages require low density of expression because you've got to put so much stuff in there just to say what you want to say. But in a light syntax language, the density of expression is extremely high. You can say a lot with just a few gestures. And because of all of that, because of that curve, my third constraint for a future language is a light grammar language. I want that domain-specific language. I want the speed. I'm going to have to deal with the landmarks somehow, which I can probably deal with by structuring the code well and extracting methods well, and maybe even using some comments. But I want the benefits on the right side. So I want a light grammar language going forward. All right, last thing. Homoiconic. And yes, I said, what the hell is homoiconic? What does that mean? Okay. A homoiconic language is a language that executes out of its own data structures. Now, the most obvious example of that is an assembly language, right? The assembly language, the machine language, is stored in machine words where all the data is stored too, and it executes out of its own data structure. The data structure is not very complicated. It's just a linear list of words, but still, the language in assembly code executes out of its own data structure. It's a homoiconic language. Are there any others? And the answer to that is yes, there is another. One other, as far as I'm aware, and that is Lisp. Lisp executes out of its own data structure. That data structure is a list, a linear list of, in this case, tokens, functions. And that means something very interesting. It means that when Lisp is compiled, and it does go through a compile phase, it compiles that Lisp code into a list data structure that could then be manipulated by another Lisp program before it executes. And we call those things macros. In Lisp, we call a program that manipulates the list structure of another program a macro. And here is a macro in Lisp, a very, very simple one. Let's say that you wanted, and look down here at the lower left, right? Let's say that you wanted to write 1 + 2 and evaluate that in fixed notation, as opposed to +1, 2, which is how you'd have to do it in Lisp, right? So is there a way to take this list here, this 1 + 2 list, and turn it into the list +1, 2, which would execute? And so we have a little macro down here. And at the bottom, you see there's a little macro. And all it does is it takes its arguments, the expression arguments, and runs it through a function called infix to prefix. And the infix to prefix function, all it does is it gathers the 3 symbols and then simply reorders them and spits them out as a list. And when you say compute up here at the upper right, okay, it simply gathers those 3 arguments, reorders them, and then executes them. The macro runs a Lisp program at compile time, which modifies the Lisp program that will run at runtime. And that makes it really interesting to make data domain-specific languages. Really interesting, because now you don't have to depend upon Lisp grammar at all. You can invent your own grammar and then compile it at macro time into actual Lisp programs. So you can make much more expressive, much more powerful domain-specific languages with that kind of a language. And so that is my 4th constraint. My 4th constraint for future languages is that they should be homoiconic. I want them to enforce all 3 paradigms. I want them to be dynamically typed. I want them to be light grammar, and I want them to be homoiconic. And at the moment, there aren't a lot of languages that conform to that, except for one that I know of, which happens to be Clojure. I do not know if Clojure is going to be the final language. I'd kind of like it to be. I don't know if Clojure will set the model for the future languages going forward, but I think it ought to. Now, might there be other languages after Clojure? Maybe. But I want future languages to conform to those 4 constraints. Whether it's Clojure or some other language, I don't know. I have a beef with Clojure. It runs on the JVM. It also runs in the browser. You can use Clojure script if you want to. But I think the final language, and I didn't put this in as a constraint, but I think the final language probably ought to run in just raw machine code. It should be natively compiled. In any case, ladies and gentlemen, the time is over. The end of my talk has arrived, and we are done with this session. I know there's a bunch of questions down there, and I will entertain those questions. But before I do, I thought Tad should come on the line and say a few words, and Angela should come on the line and say a few words. And then after that, I'll answer a few questions.
Thanks, Bob.
Tad, turn it
thank
over
you,
to
everybody, for joining us and staying with us for the full 2 hours. We appreciate your participation in the chat and attention as Bob did his great presentation on the future programming languages at the confluence of paradigms. We just want to recap some things that we said in the very beginning, where Clean Coders Studio thanks you as a sponsor, as well as Clean Coders Video, which is one and the same, but we offer 2 different services there. You feel free to access our website via the QR code on your screen, or visit us at cleancoders.com. Also, Angela, I'm sure you'll be bringing up that other slide that shows Uncle Bob Consulting, Clean Coder link that will be brought up. But on behalf of Clean Coders, thank you for joining us today on this talk that Bob has presented very well, and helped to level up the programmers across the world. So thank you, Bob, for delivering your message today. Angela, on to you.
Okay, hi everyone. Oh, we might need to, let's see, unmute you. Hi everyone, thank you so much for being here. Again, these websites are, you can visit the next webinars. We're currently doing test-driven development, which is every Wednesday. These are the Wednesday webinars. Clean Agile is coming up. Clean Architecture is coming up. You can always email me at angela@cleancoder.com with questions and seeking information about how to get Bob to come and speak to your group. And we look forward to seeing you in the future. Thank you so much for joining us.
Okay, that's me now. Okay, and I'm going to stop the share here and do some Q&A, just a little bit of Q&A. I saw there was a lot of questions down there, so I thought I'd go ahead and answer a few of them. And I'm not going to be able to get to the 68 questions. Sorry, guys, but are the slides available for the talk? We're going to make an announcement about that later. Does Uncle Bob have the new Microsoft Flight Simulator? No, I use X-Plane. Sorry. I know. Oh, how is it to fly a plane? It's great. It's one of the hardest things I've had to learn how to do, but it's terrific. I love it. You should all learn how to fly a plane. Go do that. Let's see. Nick Barton says, how much code is remaining in COBOL? Way too much. Way too much code remains in COBOL. Let's see. Adrian says, the tech industry is growing very fast. As users of those products, we can see that code behind is smelly. Do you think we will get to a moment where it will be unsustainable to write bad code? It's already unsustainable to write bad code, even though it's kind of not sustainable even today. Yes, you anticipated me there. The fact is, many companies make profit with bad code. Yes, but they would make much more profit with good code, and many more companies could make a positive profit with good code. Never forget, right? The companies that are making a profit with bad code are the minority, because there are so many companies that tried to make profit with bad code and failed. And those companies would have made a profit if they had good code. Let's see if we can scroll down here and find a question. This is an interesting one. On aerospace defense projects, and now it's scrolled out of my view. There it is. Okay. On aerospace defense projects, we were mandated to write in ADA 83 and then ADA 95. And it scrolled out of my view again. So now I don't know what the rest of that question was. I can't seem to anchor it. Okay. Well, sorry, but I can tell you one thing about ADA. Oh, there it is. In what direction are these projects going these days? I've been out of this domain for a while. I have no idea. I've never programmed in any of the ADAs. I don't know what's happening to ADA. I do know that a number of projects escaped from ADA, Defense Department project, escaped from ADA by writing waivers, and they would use C++ or other languages instead. And apparently it was possible, at least in the early days, to do that. The space shuttle, for example, right, was not written in ADA, right? So. Let's see if I can anchor a question here. Let's see. With modern IDEs, static typing languages have a huge speed benefit because of refactoring tooling. What do you think about that? Yes, that's a very good point. Static typing allows the IDE to more effectively do refactorings. That is one of the big advantages to static typing. However, the very first refactoring browser was written in Smalltalk. So it is not impossible to make good refactoring browsers in a dynamically typed language, but it is harder because you don't get all the type hints. Right? That being said, I'm still voting on the dynamic side of things. I think that's probably better. And I'm going to do, let's see, a couple more. Let's see, your language requirements are really well explained, and especially why each constraint is actually useful. To be honest, though, homoiconic felt pretty esoteric, and as a preference, can you explain a bit more? Well, the homoiconic part is esoteric, and it only becomes very useful if you're trying to write a framework that many people are going to use, and you want to create expressive shortcuts for the gestures within that framework. That's the best place I have found, right? I usually don't use homoiconicity in a normal program, but when offering a set of facilities to other people, it can sometimes be remarkably helpful to come up with a domain-specific language that's easy for them to understand and does not get in their way. So for frameworks, for really interesting domain-specific libraries, it can be really, really cool. Also for configuration data. You know, if the configuration data is really intricate and you've got to link it and do all kinds of weird stuff to it, but it's only, you know, you could express it with a few tokens. The interconnections can all be done by the homoiconic macros. Let's see, one more. Hi, Uncle Bob. What is your opinion about paradigm use cases in languages, briefly object-oriented like Go? Thank you. I love Go. I think Go is a great language. I don't think they sacrificed any of the OO paradigm, because you can still do polymorphism. You just can't do raw inheritance, and I don't normally see any reason to do raw inheritance. Oh, sometimes it's convenient, but you know, as a language, I think Go is really cool. And my favorite thing about Go is that we've all gotten used to Java and C#, and those languages are slow. And Go is like really fast. I mean, it's like rip snorting fast. So you know, get some Go sometime. Just play with Go sometime and just run a little bit of it, and be prepared to be surprised at how fast your computers really are. And with that, I think we should close it. Thank you all for your attention and for sticking around. I hope you enjoyed this talk, and we will be back with another one of these days. Bye-bye.